Okay, can hopefully hear me. Thank you very much. It's a wonderful conference with wonderful speakers. I'm going to tell you a little bit about small molecules. So we used to be very much involved into what people are talking about in this conference. So small molecules, ultracold molecules. We kind of deviated from that during the last years, and we do a lot of things which are kind of molecules in the presence of the many-body environment, but not exactly like optical lattices and such things. So, for example, we're interested in molecules in quantum fluids, like in superfluid helium droplets, and to introduce so-called angulon quasiparticle to describe it. And then we're using this model quite beyond molecules, for example, to study Einstein-de Haas effect and transfer of angular momentum from electron spin to the crystal lattice. We're also interested in topological properties of kicked molecules that I'm going to focus on today, also on this part. So we are working on molecules trapped in real solids, like perovskites, hybrid organic and organic perovskites, where molecules are probably responsible for some interesting properties, like photoelectric properties that make them good materials for solar cells. And finally, we're working with quite large molecules and spin transport through these molecules, trying to explain the so-called chirality-induced spin selectivity effect. I'm going to be very happy to tell you about these parts later at lunch. But for now, quite work. So I'm going to focus on very small molecules, and it's probably a wrong audience to show this, but we know that the most complex molecules are the diatomics, and it's still surprising how much you can find after 100 years in this type of species. So what we're in particular interested in is to try, I just want to spend some time on this slide so you don't understand me wrong. So we don't aim to do quantum simulation. And in general, we believe that maybe we should simulate a little bit less and study physics a bit more. So what we're trying to see whether we can find topological properties in simple systems like molecules, similarly to how it has been done in condensed matter physics, right? So we're not doing, topological stuff in molecules because it's hot there, but we're trying to understand why it's hot there, and maybe we can also do something similar, which would have applications for chemistry. So why it is important to have topological kind of considerations in solid-state physics. So one of the big breakthroughs, and there was a Nobel Prize for that to Haldane and others, is the discovery that you can classify states of matter not only through order parameter like heat capacity or magnetization or some symmetry, but also through topology. And if you have a very complicated system like a crystal, or in our case a molecule, it is very nice to have some exact topological invariant. If you could say, it's a mess, it's a lot of atoms, a lot of degrees of freedom, but you can say, it's 1, 2, or 3, or 4, like we do with, for example, rotational states or vibrational states, but in a kind of more complex sense. So what we topological physics, I also took this picture right now. So, topology, Berry phase, and so-called geometric phase. So Michael Berry doesn't like when it's called after his name, as far as I know. So it has been also quite an old thing. So I'm going to tell you about a lot of old things kind of combined together. So geometric phases are quite old, and one of the examples is the Floquet pendulum. So if you move on a curved surface, you do parallel transport, you don't end up in the same orientation, like if you transport some vector, for example. So it can be illustrated here. So this is pretty much what happens in a similar way with the Floquet pendulum. And topological ideas were around in physics and chemistry for a long time. So they were discovered before Berry, actually, in optics, and after Berry. So you can you heard of topological insulators recently. You have topological defects, skyrmions, vortices. In chemistry, for example, there are conical intersections that have been studied for a very long time. If you have a potential surface crossing, then you go around, you pick up some phase. This is all very well known. And what we try to do here is to directly match the ideas of what you have, in solid state in terms of like topology on a lattice and in terms of a structure of a single molecule. So loosely speaking, what we're trying to do is to take a single molecule and to consider just one molecule with its rotational states as a lattice on which rotational population is hopping. So it's a single particle problem for now. So you have rotational states, and if you couple them with a laser field, you will have hopping between them. Well, this again has been also an extremely well-studied problem. It's called, a kicked rotor problem. It goes back to the 60s, probably to the 70s, and it has been studied a lot that if you periodically kick a rotor, like a molecule in this case, you can have different regimes. So, for example, you can have periodic kicking whose frequency matches the rotational period. Then you can have a quantum resonance, and if it's off, you will have a dynamical localization, and there is quantum chaos, and so on in the system. And we're actually focusing on this regime where you have a quantum resonance. So you're periodically kicking such that the population of molecular rotational population is hopping on this lattice. And then it turns out that you can perform this direct mapping. So you can imagine that you are periodically kicking a molecule with a laser pulse. Molecule has rotational states. Then the laser coupled these rotational states. So it becomes like a copy. It's not as trivial as I'm explaining because there are a lot of things swept under the rug that one actually needs to show. For example, as you know from spectroscopy, when you calculate some transition matrix elements, they're usually different between different states. But when I can actually show that for reasonably large angular momentum, they kind of converge to be very similar. So you can actually map it onto some kind of isotropic lattice. And then you can work with it the same way you're working with normal solid state system. So you remember maybe from your university course that if you have a solid, periodicity in space allows you to use nice things like Bloch theorem, for example, and then you can introduce momenta, you have band structure, and so on. In this case, we have a Hamiltonian which is periodic in time, not in space. And instead of Bloch theorem, we're using Floquet theorem for systems periodic in time as opposed to in space. Although, again, a lot of things that one needed to kind of show here. For example, people were also doing, mathematical physicists working with kicked rotors have been doing it for many years, modeling lasers with delta pulses. It is actually quite tricky, and a lot of things were kind of neglected. We have analyzed it in more detail here to show when you can do that and when you cannot do that to kind of be reasonable with respect to experiments. But in any case, instead of the Hamiltonian, what one does in Floquet picture, you analyze the evolution operator, and then you can get eigenstates of the evolution operator and pretty much treat them the same way as one does with bands in regular crystals. So you have some kind of Floquet bands instead of Bloch bands in this kind of quasi-momentum space. So if you take one molecule, so this is the simplest case, we studied different cases, but this is the simplest one where you see interest in physics. So if you take a molecule and you kick it with such type of Hamiltonian, so it's two different laser fields, and the fields are parameterized by some parameter alpha, then you can get this quasi-momentum space, quasi-momentum states in Floquet space, and you have these bands that very much remind us of bands in the solid state, right? In these bands, you actually observe different types of states. So there are usual bulk states, usual delocalized states. So for molecular physicists, it means that you have a state which is delocalized over all rotational states. It's like, traveling somewhere. So you're periodically kicking the molecule, and population is just wandering around all rotational states. You have also H states, which are localized. So in the case of the simplest, for example, diatomic molecule, you would have then localized state sitting on L equals 0. So it will be on the edge of your crystal, which is the ground rotational state. And also you have these features here and also here, which are topological Dirac cones, similar to the models of like of spinless graphene, for example. You can go around them and you pick up a phase of pi or minus pi. So we came up with some protocols how to realize it experimentally, so how to detect them experimentally. So one needs to be kicking the molecule, and you can change the intensity of the fields in some particular way, such that you go around this Dirac cone in the parameter space, and then you see the change in orientation or alignment of the molecule. For example, here you can see that orientation of the molecule flips. So you will see that the molecule changed the orientation, which would mean that well, that would be easily visible in experiments on Coulomb explosion, for example. So what these people do, they kick the molecule and then they ionize it, and charges repel each other, and you measure real space positions of atoms. So in this case, it will be quite easy to see. So let me summarize this part. So we have shown that one can observe some topological properties of even single molecules if you kick them with periodic laser pulses. Now we would like to go to more complex systems, maybe like get some kind of real topology in the sense of what people do in the solid state, get some Chern number, and maybe consider more complex lattices, like more complex molecules will have more types of states. Also interacting systems, like you can put these molecules on a lattice or try to put them maybe in more molecules, in like 2 molecules in a trap and see what happens, or some weakly bound complexes. We're working on braiding of cones. I mean, this is more on the kind of crazy side experimentally, but theoretically one could see in principle that in Floquet systems you can observe some, most likely, we're not there yet, but there are interesting signatures of some braiding of cones and doing some very weird topological things, like some getting some Euler number and so on. And finally, our kind of big picture goal, which is here quite speculative, is to try to introduce some kind of topological classification of systems in chemistry, such that you would say, like you have a molecule, and like for example, in this case, like if you kick it with a laser, it behaves like like it has that type of topological quantum number, and then you can put, I don't know, some CO and DNA in the same topological class. It's not going to happen, but I mean, like if you can understand chemistry better by additional classification of molecules with respect to their kind of topological classes in that way. And maybe, of course, like I don't want to speculate about applications to topologically protected quantum computation or something, but maybe other people would speculate about it. So I would like to switch gears now and tell you a little bit more about small molecules in helium. So we are doing it a lot, and it's a very mature field, and we're trying to describe the dynamics in particular of molecules trapped in superfluid helium. So these are kind of cold-ish molecules. It's 0.4 Kelvin approximately, so it's not at the level that people here are interested in, but these molecules can be anything. So they can trap peptides and huge biological molecules, nanoclusters, some magnetic nanoparticles, almost anything starting from atoms and diatomics. And people were doing it for many years. They were trying to understand to understand the structure of molecules, because they're quite cold. And if you do spectroscopy, like in helium or in the gas phase, so why is it possible to do spectroscopy at all? Because we have selection rules, right? Pretty much. Because if you wouldn't have them, you wouldn't be able to interpret your spectra. But on the other hand, probably the most annoying thing about spectroscopy is also the selection rules. Because imagine if you have a cold molecule, so to study the molecular structure, you want it to be cold, right? So you don't have Doppler shifts, collisional broadening, and so on. But if you prepare a molecule in a at a very cold temperature, it's going to be in the ground state, close to the ground state, and selection rules won't allow you to climb up the rotational vibrational states because you can go, one at a time. While you're getting such nice vibrational spectra for like room temperature in, for example, ultracold molecules or molecules in helium droplets, you will have only a few peaks. And so that kind of influenced the whole field a little bit of molecules in helium droplets, because people were measuring only the transitions between the ground and first excited rotational states, like a few of them. And so it was kind of common knowledge in the field that you can approximate the rotational energy in helium droplets in a very similar way you do in the gas phase. So you would say that there is some rotational constant, and it is different. So it is a bit larger than in the gas phase. Moment of inertia is a bit larger, rotational constant is a bit smaller than in the gas phase. And sometimes, like, you would add a second term that you would say that centrifugal distortion is also getting larger compared to the gas phase. But at helium temperatures, you cannot have states more than J equal 5 populated. So in the dipole approximation, you can maybe probe 6 of them, right? And the way to go around that and to actually study how highly excited rotational states of molecules behave in the presence of some quantum liquid like superfluid helium is to do so-called rotational coherence spectroscopy. So the idea is that, well, it has been used in several fields before, but the idea is that instead of doing resonant transitions, you do an off-resonant excitation. So you have a short laser pulse, like almost a delta function, that suddenly aligns the molecule, so it squeezes the angle. And uncertainty principle tells us that squeezed angle means that you populate a lot of angular momentum states. So you create a wave packet that evolves in time, and you see revivals of this wave packet. So you measure time dependence of rotational evolution, you Fourier transform it, and you see the peaks that corresponds to transitions between different states, which can be also quite high in energy and angular momentum. Good things here is that, well, apart from accessing highly excited state, is that it also works for non-polar molecules. So if you have a strong enough laser, it also couples to homonuclear molecules, for example, that are blinds to regular dipole excitations. And here is kind of a proof of principle thing. So, in this paper, Henrik Stapelfeld, it's the leading experimental group in Aarhus. So they performed this measurement for OCS, and for OCS it has been known because you could also measure it using spectroscopy. So this is just evaluation of the spectroscopic constants. And for the first time, it was possible also to evaluate it for CS2 and I2 because they are symmetric and don't have a dipole moment. But in this case, there is no deviation from this formula that I've shown you. That still works. So you can still approximate to this type of rotational states using this formula, the rotational spectrum. Similar thing was done with for D2, and it was observed that it's rotating almost freely in helium by the group of Jian Wu. And here, of course, it was a very complicated experiment, and every time we're collaborating with such experimental groups, I feel that, I have to show that meme. It ain't much, but it's honest work to show why nothing changes if you put it in helium. Does not that much work actually, but what's most interesting, what was actually exciting for us, at least in the beginning, is that you can access really highly excited rotational states. And then you will see clear deviations from what people believed it was true in the community. I don't know whether they wanted to know that. So you can apply very kind of intense laser fields to populate a lot of rotational states. And then you do Fourier transform, you analyze it, and you see for CS2 and I2 that So the theory and experiment, it's like based on our angulon theory, they agree quite well. And if you have this fit, if you apply this fit using B and D constants that people believe was enough, you see a deviation, and of course it will get unphysical at some point, go to negative energies and so on. So that was already something. And what's nice about simple theories, well, first, I mean, our theory is quite qualitative, so we cannot so it's not ab initio in some sense. So we have some input parameters, and then we predict a lot of other things, but also for to do the dynamics of molecules in helium, or to do like highly excited states, it is extremely challenging to use exact techniques like Monte Carlo type of approaches. So here we don't have much choice but to use some kind of models. But also a good thing about models is that you can actually understand a lot of what's going on. So for example, you can plot the transfer of angular momentum between the molecule and the superfluid, and notice that the dependence, like the change in angular momentum, is actually giving you the rotational spectrum, like the differential rotational spectrum. So you can exactly see that, you know, the deviation of the spectrum from the gas phase one is like is coming from the transfer of angular momentum to the superfluid. So one could directly analyze it in simple terms. Now, actually, nobody have more time, but I don't have too much more to say. So I want to summarize here that we studied highly excited rotational states of molecules in helium, and we observed substantial deviations from this type of behavior that believed to be like sufficient. This also needs to be taken into account in some other experiments that, you know, people do, for example, optical centrifuge, where they spin a molecule very fast by spinning polarization of the laser. They try to do it in helium, and it was super challenging, so it hasn't worked yet. And we think we understand that because of that, what we've shown here, it shouldn't work. So, I mean, it will work, but you need to take all of that into account. So you cannot just do the same as in the gas phase. And I wanted to highlight, I didn't talk about it here, but we also observed, so Henrik Stapelfeld observed first two-dimensional rotation. We believe it's first two-dimensional quantum rotor ever, as far as we know, so it kind of sounds funny, but two-dimensional rotor, just a planar rotor, it's a nice model, but everything rotates in 3 dimensions, right? And for example, if you put molecules on the surface, they usually do not rotate if they're chemically bound or like have some discrete positions, or extremely light molecules like H2 on some surfaces, they rotate in 3 dimensions. So it's possible, but it's still not a planar rotor. But surprisingly, if you put a molecule on the surface of a superfluid helium nanodroplet, so some molecules sit in the center, some go to the surface. So if you take those that sit on the surface, some of them rotate as real 2-dimensional rotors with the corresponding energy spectrum. And they observed it for the first time, and we also tried to explain it here. Okay, I'm coming from this institute, so it's IST Austria. It's located next to Vienna, so we're actually also looking for faculty, but also for PhD and postdocs in my group. Thank you very much. Of course.
You should seat in the first row.
Yes,
you want the Russian question or the nice question? No, for your outlook on the first part, you had mentioned combining this with interactions, but at least to me it's very non-obvious what interactions would even look like in this sort of Floquet system. So what do they look like?
Well, they will modify your lattice, for example, and then you would have well, you either will have like a joint state of eigenstates on which you will have like a joint lattice, which will be maybe highly entangled or something. But I mean, so I think they can do a lot of things, from destroying everything to creating something interesting. I mean, sorry, it's super vague, but
can you even think about the interactions like local in this?
No, but if you just put 2 molecules, right? It's like 2 lattices with some weird coupling between them. I don't mean anything like weird. It's just 2 molecules. interacting, and they will have some state on which this like effective particle will be hopping, right?
Yeah, I guess my question is about how the interaction structure on that lattice. Like, are they infinite ranged? Are they local? What's the?
I see. So what I meant is the interactions between kind of different lattices. You know, if you have different molecules, the lattices will be modified, right? And then, yeah, it's not interactions between particles on the same lattice. I hope it helps.
More questions? Okay. If not, then let's thank the speaker again, but let's not move yet.